One, two, three.
Go. Um, Hello there. Luciddeamer, domain-free generation of... Nah, don't laugh. Why are you laughing, bro?
Hello, this is the
Domain...
Agora Daily Paper Clip, and now we would like to introduce to you the LucidDreamer, domain-free generation of three-dimensional Gaussian splatting scenes by many noteworthy individuals from the Seoul National University of Seoul, Korea. Now, let us commence with our formal review of this paper.
With Kai, V, Evelyn, Plenty. From Agora. Let's go. Point cloud initialization, 3D Gaussian splatting world model. We got a lot of pictures right now. So
Okay, so let's analyze this. So the inputs is a text prompt, and then this is fed into a pre-trained image diffusion model, maybe stable diffusion. Then you have monocular depth estimation, which will estimate the depth of the image, and that's what this looks like. So we take the pre-trained image diffusion model. Then we take the depth estimation. Then we apply 3-dimensional Gaussian splatting world model, which creates kind of like a panoramic picture. Like it adds like a panoramic learning. It kind of looks like a panorama.
Yeah, it kind of looks like that.
So we have LucidDreamer and
so it dreams.
No, bro. Nah, it does not. So we have
I get
LucidDreamer.
back.
So the next thing that happened is PI key KPIO3. So then we have the lucid dreaming module, which will align, navigate, and then dream again. The output will be an image that is generated. It's a navigationable 3D scene. So if you look at the second row of images, you can see a nice dude. That place looks fun to be in. I would love to be in this place.
Yeah.
I'll just jump at the lake. All right, we have some more depth estimation, RGB, and alternative views of some other angle of the thing. All right, start reading up Figure 1, introducing LucidDreamer.
Introducing LucidDreamer. We developed LucidDreamer, a general framework for generating multi-view, consistent, and high-quality 3D scenes from various input types: text, RGB, RGBD. After the initial point cloud is created by lifting the RGBD image, LucidDreamer maintains and expands its world model by repeating two operations: dreaming and alignment. The 3D scene is finalized through optimizing a Gaussian splatting representation. Abstract. With the widespread usage of VR devices and contents demanding for 3D scene generation techniques become more popular, existing 3D scene generation models, however, limit the target scene to specific domain, primarily due to their training strategies using 3D scan dataset that is far from the real world. To address such limitations, we propose LucidDreamer, a domain-free scene generation pipeline by fully leveraging the power of existing large-scale diffusion-based generative models. Our LucidDreamer has two alternate steps: dreaming and alignment. First, to generate multi-view consistent images from inputs, we set the point cloud as a geometrical guideline for each image generation. Specifically, we project a portion of a point cloud to the desired view and provide the projection as a guidance for inpainting using the generated model. The inpainted images are lifted to 3D space with estimated depth maps composing a new points. Second, to aggregate the new points into 3D scene, we propose an aligning algorithm which harmoniously integrates the portions of newly generated 3D scenes. The finally obtained 3D scene serves as initial points for optimizing Gaussian splats. Luciddeamer produces Gaussian splats that are highly detailed compared to the previous 3D scene generation methods, with no constraint on domain of the target scene. Introduction. With the advent of commercial mixed reality platforms and the rapid innovations in 3D graphics technology, high-quality 3D scene generation has become one of the most important problems in computer vision. This requires the ability to create diverse and photorealistic 3D scenes from any type of input, such as text, RGB, RGBD images. There are efforts to use the diffusion model in voxel, point cloud, and implicit neural representations to generate 3D objects and scenes directly. 112560 is the dimensions, but the results show low diversity and quality due to the limitations in training data based on 3D scans. One way to cope with the issue is to leverage the power of pre-trained image generation diffusion models, such as Stable Diffusion, to create. Oh, those are references, my bad. To create diverse, high-quality 3D scenes. Yeah, such a big model creates plausible images with a data-driven knowledge learned from the large-scale training data, although it does not guarantee multi-view consistency between the generated images. In this work, we propose a pipeline called LucidDreamer that utilizes Stable Diffusion and 3D Gaussian splatting to create diverse, high-quality 3D scenes from various types of inputs such as text, RGB, RGBD inputs. Following the pipeline of Luciddeamer, a unified large point cloud is generated by repeating the two processes named dreaming and alignment alternatively. Before beginning the two processes, an initial point cloud is generated by the initial image and the corresponding depth map. Dreaming process includes the generation of geometrical consistent images and the lifting of these images into 3D space. We first move the camera along the predefined camera trajectory and project a visible region of point cloud in the new camera. Coordinate to the new camera plane. Then the projected image is put into a Stable Diffusion based inpainting network to generate the complete image from the projected one. A new set of 3D points are generated by lifting the inpainted image and the estimated depth map to the 3D space. Then the proposed alignment algorithm seamlessly connects the new 3D points to the existing point cloud by slightly moving the position of the new points in the 3D space. After a large point cloud generated by repeating the above processes, a sufficient number of time is obtained. We use it as the initial FM points to optimize Gaussian splats. The continuous representation of 3D Gaussian splats removes the holes generated by depth discrepancy in the point cloud, enabling us to render more photorealistic 3D scenes than traditional representations. Figure 1 shows the simple process of Luciddeamer and a 3D generation result. Luciddeamer exhibits significantly more realistic and astonishing results compared to existing models. We compare the generated 3D scenes conditioned with an image from ScanNet, NYU depth, and Stable Diffusion and show better visual results across all datasets. Our model is capable of generating 3D scenes across diverse domains, such as realistic anime, Lego, and indoor and outdoor. Not only does our model support various domains, but it also accommodates the simultaneous use of diverse input conditions. For example, by conditioning an image and text together, it generates a 3D scene based on the text but also includes the image. This alleviates the challenges associated with creating the desired scene solely from the text, moving away from generating samples exhaustively. Furthermore, our approach also allows for the change of the input condition while creating 3D space. These capabilities offer opportunities to create a wide range of 3D scenes, inspiring creativity. In summary, our contributions are as follows. We introduced LucidDreamer, a domain-free, high-quality 3D scene generation, achieving better domain generalization in 3D scene generation by leveraging the power of stable diffusion, depth estimation, and explicit 3D representation. To generate multi-view images from Stable Diffusion, our dreaming process established point cloud as geometrical guideline for each image generation. Subsequently, our aligning process harmoniously integrates the generated images to form a unified 3D scene. Our model provides users with the ability to create 3D scenes in various ways by supporting different input types such as text, RGB, RGBD, allowing simultaneous use of multiple inputs and enabling the change of the inputs during the generation process. Related work.
Would you like to? Evelyn, are you with us?
What?
Evelyn.
I am. I've been keeping silent because there was a lot of noise on my mic. I'd be happy to read. Where shall I pick up?
Related work.
Were you going too fast?
No. I just want to give someone else a chance to read.
Thank you, V.
Okay.
3D scene representation. Representative methods for expressing 3D scenes include explicit methods such as point cloud, mesh, and voxel. These are widely used because they allow direct and intuitive control of each element and enable fast rendering through this rasterization pipeline. However, they need a large number of elements for detailed expression because of their simple structure. Complex primitives such as cuboid, Gaussian, ellipsoid, superquadrics, convex hull, and polynomial surface were developed for more efficient expression. Although primitives have increased expressive power for complex geometry, it's still difficult to express realistic 3D scenes because of simple color representation. Recently, there have been works to express more detailed 3D scenes using neural networks as implicit expressions. They trained a neural network to express the scene, creating the desired properties in 3D coordinates, such as sine distance function, RGB alpha. In particular, neural radiance fills showed that it was possible to optimize photorealistic 3D scenes for multiple images through volume rendering, but the scene implicitly stored in the network form is difficult to handle and slow. To improve this, the subsequent studies attempted to use volume rendering in explicit expressions. By using the locality of structures such as sparse voxels, featured point clouds, multi-level hierarchies, tensor, infinitesimal networks, triplane, polygon, and Gaussian splats, they greatly improved the training and rendering speed. In particular, 3D Gaussian splatting uses the concept of Gaussian splats combined with spherical harmonics and opacity to represent complete and unbounded 3D scenes. It supports not only alpha blending, but also differentiable rasterization, resulting in fast, high-quality 3D scene optimization. This structure is essential for our generation model, which cannot determine the bounds of the scene due to sequential image generation and plays a role in making the scene complete. And I just want to say that we discovered Gaussian splatting in August, and this is November. 3D scene generation. Inspired by the early success of generative adversarial network, GAN, in image generation, similar attempts are made in 3D creation. Creating a set of multi-view consistent images or directly creating voxel or point cloud were studied. However, they suffer from GAN's learning instability and memory limitation in 3D representation, limiting the generation quality. Encouraged by the recent success of diffusion in the field of image generation, there are many attempts to introduce the diffusion model into 3D representation, such as voxel, point cloud, triplane, implicit neural network. They use object-centric coordinates because of their nature and focus on simple examples. Some generative diffusion models overcome this problem by using a mesh as a proxy and diffusing in the UV space. They create a large portrait scene by continuously building the mesh or create indoor scenes and more realistic objects. However, their performance falls short of foundation models because they involve training a new diffusion model in a different representation space, which is limited by data availability and computational resources. In comparison, our model leverages the power of the foundation model to generate diverse images and creates reliable 3D scenes through depth estimation and optimization. What was the name of that paper we read about satellite diffusion models? That was a while ago, like late September, like eons ago. Anyway, I'm sorry, I'm laughing too hard. 3. Method. While the range of target scenes of existing scene generation models is strictly restricted due to the limitations in training dataset, LucidDreamer can generate even more realistic, higher resolution 3D scenes with much more general input conditions. For instance, LucidDreamer can generate text-relevant scene if only the text prompt is given. Also, the style of the input image is maintained along the scene, while existing models keep producing scenes that are similar to the style of the training dataset, not the input image. The pipeline of LucidDreamer is broadly divided into 2 stages: point cloud construction and Gaussian splats optimization. During the first stage, an initial point cloud is formed from the input image, and the area of point cloud is expanded to create a large scene using stable diffusion, inpainting, and monocular depth estimation. Then the point cloud and the reprojected images are used to optimize Gaussian splats. By representing the scene with Gaussian splats, we can fill the empty space that appears in the point cloud due to the depth discrepancy. Any questions about that?
No. Then the point clouds and the are used to. I'm just writing some of this down.
Okay.
Used to optimize Gaussian splats. We should read the Gaussian splats paper and try to implement it.
Yes, we should.
You can fill the empty space that appears on the
Yep.
Okay, let's continue.
Okay. Point cloud construction. To generate multi-view consistent 3D point cloud, we create the initial point cloud and aggregate the points by moving back and forth between 3D space and the camera plane while moving the camera. The overall process of point cloud construction is illustrated in Figure 1. Have you discussed Figure 1?
Yep. If you want to discuss it again, we can go back.
Okay, introducing LucidDreamer.
Okay.
Yeah. Section A is the point cloud initialization, which can use either a text prompt through a pre-trained diffusion model and a monocular depth estimation. Both the pre-trained image diffusion model and the depth estimation are locked layers. The second one is Area B, which shows a 3D Gaussian splatting world model, which has different and arc monocular viewpoints, so that little pink camera trajectory, which is then aligned with LucidDreamer. There's a navigate to dream and align circle. The iterative navigation and dreaming feeds a generation of an image back through, which is also locked, and an estimation, and the LucidDreamer iterates through navigating the space. D shows scenes of generated navigable 3D scenes which look very consistent from view to view, and the alternate views also look very consistent from view to view. This is absolutely amazing. LucidDreamer is a general framework for generating multi-view consistent and high-quality 3D scenes from various input text types, text, RGB, and RGB with depth. After the initial point cloud is created by lifting the RGB with depth image, LucidDreamer maintains and expands its world model by repeating two operations, dreaming and alignment. The 3D scene is finalized through optimizing a Gaussian splatting representation. Okay. Continuing 3.1 point cloud construction. To generate multi-view consistent 3D point cloud, we create the initial point cloud and aggregate the points by moving back and forth between 3D space and the camera plane while moving the camera. The overall process of point cloud construction is illustrated in Figure 1. Initialization. A point cloud generation starts from lifting the pixels of the initial image. If the user gives a text prompt as input, the latent diffusion model is used to generate an image relevant to the given text, and the depth map is estimated using the monocular depth estimation models such as Zoe depth, which denote the generated or received RGB image, and the depth map as big bold I0, which is an element in R to 3 times height times width, and big bold D0, which is an element in R, H times W, where H and W are height and width of the image. The camera intrinsic matrix and the extrinsic matrix of I0 are denoted as K, which is the camera intrinsic matrix, and P0, which is the extrinsic matrix. For the case where uppercase I and uppercase D0 are generated from the diffusion model, we set the values of K and P by convention regarding the size of the image. From the input RGB with depth image, that is I0, D0, we lift the pixels into 3D space, where the lifted pixels will form a point cloud in a 3D space. The generated initial point cloud using the first image is defined as P, script P0, which is equal to phi2 mapped to 3 for parameters tuple of I0 and D0 and K and P0, where the mapping phi2 to 3 is the function to lift pixels from the RGB with depth image ID to the point cloud. Any questions about that?
Nope.
Okay. Point cloud aggregation. We sequentially attach points to the original point cloud to create a large 3D scene. Specifically, we set the camera trajectory with length n, where P, I, indicates the position and pose of the camera in the ith index, then inpaint and lift the missing pixel in each step. Here, the generated points should satisfy two conditions. The images projected from the points should have high perceptual quality and be consistent with image parts produced from the existing points. To achieve the former condition, we borrow the representation power of the stable diffusion in the image inpainting task. Navigation. At step I, we first move and rotate the camera from the previous position, pi minus 1, to pi. We change the coordinate from the world to the current camera and project to the camera plane using k and pi. Any questions about that?
No.
Okay. Dreaming. We denote the projected image at camera P, I, as II, or is that a hat I? Yeah. An estimated I at I.
It's cap. It's called I cap suffix or like I cap I.
So when there's an angle over a large, when there's an angle over a large letter, it's called hat. Since the position and the pose of the camera are changed, there would be some reason that cannot be filled from the existing point cloud. We define the mask MI to discriminate the region that is filled by existing points in I hat I. Specifically, the value of M sub I is 1 if the corresponding pixel is already filled, or 0 otherwise. The stable diffusion inpainting model, script S, is executed to generate a realistic image I sub I from the incomplete I hat I and the mask MI. The corresponding depth map D hat I, is estimated using the monocular depth estimation network, script D. Here, the monocular depth estimation model can only estimate the relative depth, and the depth coefficients from the relative depth to the actual depth can be different between images. If the depth coefficients are different, the lifted 3D point clouds in the two generated images are not connected and are spaced apart. We estimate the optimal depth scale coefficient D sub I that minimizes the distance between the 3D points of the new image and the corresponding points in the original point cloud P I minus 1. Then the actual depth map D sub I is calculated by multiplying the coefficient D sub I to the estimated depth map D hat sub I. Any questions about that?
Interesting.
No.
Okay. So equation 2 is basically how this is done. We have I sub I equals S for I hat, which is the estimate of I, and the mask M sub I, comma, D estimate I, which equals D of I, D script I of I, and D, which equals little d sub I times the estimate of big D sub I. So they say this is only one equation, but and there's a comma at the end of that. So I think there's a tuple here with at the end. But it also appears like this is two equations, one for I sub I and one for D sub I. So I'm going to treat it as two equations. D sub I is the argument for D, for the function which is the sum from m equals 1, mi equals 1, for the measure of the lifting function for I sub I, D times the estimate I, and K and Pi minus Pi minus 1 in 1. So that will be the slight variation in change due to camera position. Here M sub I equals 1 implies that the distance of point pairs in the overlapping regions is used for estimating D sub I. Any questions about that?
explain it in simple English?
So we have a problem where when you have a Gaussian splat, sometimes the points don't have values. And so the problem is we have this point cloud where we need to have values at a particular distance in order to be able to represent the object at that distance. So what this is doing is essentially creating a mask where some of the pixels have a value and some of them do not have a value. We only want to use inpainting on those pixels which don't have a value. So what this mask does is say that when we lift from 2D into 3D, we have an image, we have a mask, we have a camera position, and so we want to generate only those pixels which need to be generated, and we're using stable diffusion to generate them. Any questions about that?
Negative.
No.
Okay. I'm going to continue. Using the image and the corresponding depth map, I sub I, D sub I, we lift the pixels into 3D space. Here we note that only inpainted pixels of I sub I are lifted to prevent points overlapping and mitigate the inconsistency problem. The output of dreaming, script p hat I, can be calculated as script p hat I equals the lifting function for I sub I, D sub I, given m sub I equals 0, that is the pixels we know, for k and p sub I. That's equation 3. Where I sub I, D sub I, given m sub I equals 0, indicates the inpainted region in the RGB depth image. So they use only the reliable portion to project into 3D space to avoid image drift. And then they inpaint to fill in the image so it looks good enough, because otherwise it would have holes in it.
Alignment.
Okay, alignment. Compared to the way that trains a generative model to generate both RGB and the depth math at once, such as RGB-D2, the depth math estimated by off-the-shelf depth estimation method is more accurate and generalizable to various situations, since off-the-shelf methods are trained on large and various data sets. However, since D0 through Di-1 is not considered when estimating Di, inconsistency problems occur when we add new points, p hat sub I. To overcome this problem, we move the points of p hat I in 3D space to attach the 2-point cloud, pi-1 and p hat I, smoothly. Specifically, we extract the region where the value of the mask placement changes. That is, the delta m sub I is greater than 0. The magnitude of delta m sub I is greater than 0. To find the corresponding points to that region in both pi-1 and p hat I. Then we calculate the displacement vector from p hat I to pi-1. However, moving the points in a naive way may distort the shape of the lifted point cloud and make a misalignment between the point cloud and the inpainted image. We mitigate the issue by giving the restrictions for moving the points and using the interpolation algorithm to preserve the overall shape of the points. First, we force each
Let's read the algorithm.
Point in padding from the... Okay. Do you want to do that?
Would you like to?
I can. Okay. Algorithm 1, constructing the point cloud. It takes two inputs, a single RGB depth image, I0 and D0. Also input is the camera intrinsic K and the extrinsic P sub I for I equals 0 through N, where N is the number of scenes to be generated, I assume. I will go back and find out what big N is. I don't see it, but that's the best guess I have. Output is a complete point cloud, script P sub N. P0 is set to the lifted 2 to 3 dimensional function of I sub 0 and D sub 0, that is the initial image, the camera intrinsic and the extrinsics at 0. We loop through I from 1 to N, which will be the number of scenes, I'm assuming. I hat I and the mask sub I are set to the lifted value 3 back down to 2, so there'll be both a lift from 2 to 3 and a descent from 3 back down to 2. This is the descent from 3 back down to 2 for Pi minus 1 for the camera position and the extrinsics. So we generate the next image based on a change from 3 back down to 2. I sub I is then set to be the splat, stable diffusion of the I mask, I estimate sub I, and the mask and the depth, which is also assigned from the depth function of the I sub I. And then the D sub I is set to 1. And while not converged, which is the Gaussian portion of this, we're looking for this to converge to a stable image. Then P hat I is set to the lifting function 2 to 3 for the image I at the scaling factor D and the depth map I plus the camera position and the extrinsics. The loss function D is set to 1 over the magnitude of the mask, which equals 1, times the sum of the mask equals 1, magnitude of P hat I minus P hat minus Pi minus 1 sub 1. So the loss function is how far off are we for the masked points. And then we calculate the delta of D and times the loss function, and then D sub I is assigned D sub I minus the alpha channel times the delta of D times the loss of D. And that will converge. We will gradually iterate on a value which will be appropriately close to the value we want, and that is convergence. And then the depth map, D sub I, is assigned the convergence depth map value, little d sub I, times the estimate of d sub I. And then script P hat eye is assigned the lift from 2 to 3 of the image depth map given the mask is 0, camera times extrinsics, and then P sub I is given the value P sub I minus 1 and the union with the weights of P sub I hat. Does that make sense? The final equation in the algorithm is explained in equation 4. I'll keep going. First, we force each point in P hat sub I to move along the ray line from the camera center to the corresponding pixel. We find the closest point to the corresponding point in P I minus 1 along the ray line and report how much the depth changes are caused by the movement. Using the constraints, we preserve the contents of the RGB image I sub I, although moving the points in 3D space. Next, we assume that the depth does not change at the opposite end of the mask boundary region. Then, for the points that do not have their ground truth counterparts, for example, m sub I equals 0, we calculate for each pixel how much the depth value should change using linear interpolation. By interpolating smoothly, the mismatch among the pixels caused by the drastic movement is alleviated. The aligned points are combined with the original one, where P sub I equals P I minus 1 union of the weights for the estimated P sub I, where we denote calculating movement and an interpolation as the script W. We repeat the process n times to construct the final point cloud P sub n. By reprojection, P sub n provides high-quality and multi-view consistent images. The whole process of constructing P sub n from the initial image K and P sub I for I equals 0 through n is written in algorithm 1. Any questions about that? You could definitely write this kind. Figure 2. Intermediate images during point cloud generation. And final 3D output between different inputs. We generate 3D scene from different input types, text and RGB image. The input image in the first row is generated using stable diffusion. Our model is capable of generating consistent images, high-quality 3D scene, regardless of input type. So the first row here is text generated, the playground in a residential area with abundant street trees, cars parked on the road, and single-family homes surrounding the playground. And stable diffusion generates a pretty good image. The depth map is shown in the lower right-hand corner of the image. In this, in the next column, we have the next image, which is I sub 1, which is again a slightly different scene camera view of the same scene with a different depth map and view onto what appears to be a consistent rotation of that scene. A variety of additional images are generated by modifying the camera, which would be moving in 3D space. And then the generated 3D image is shown at the end, which looks to be a larger 2D photograph of a pan through of the initial generated stable diffusion image from the text. This is really amazing. This is really amazing. They named it very well. This is just like dreaming. The sub-images all the way along are consistent. I don't see any tearing. I don't see any holes. I don't see any distortions. The camera appears to be consistent. The color is consistent. The textures are consistent. This is really, really well done. (3.2) Rendering with Gaussian splatting. After the point cloud is created, we train 3D Gaussian splatting model using the point cloud and the projected images. The center of Gaussian splatting points are initialized by the input point cloud, and the volume and position of each point is changed by the supervision of input ground truth projected images. We use the generated point cloud P sub n as the initial SFM points. Initialization with P sub n will boost up the conversions of the network and encourage the network to focus on generating the details of the representation. For the images to train the model, we use additional M images as well as N+1 images for generating the point cloud, since the initial N+1 images are not sufficient to train the network for generating the plausible output. The M new images and the masks generated by reprojecting from the point cloud P sub n by a new camera sequence of length M is denoted as P sub n+1 through P sub n+m. Equation 5. I sub I, comma, M sub I is equal to the downsampling of theta 3 down to 2 function for P sub n, camera position and extrinsics at I, comma I, which equals M+1 all the way through to M+n. We note that we do not inpaint I sub I when optimizing Gaussian splats. Instead, when calculating the loss function, we only consider the valid image region where the mask value is 1. It prevents the models from learning the wrong details of the reprojected images. Since each point is represented as a Gaussian distribution, the missing pixels when training the model are naturally filled, and the rasterized image after the training becomes plausible. This is so amazing. Experiments. 4.1 Experimental Settings, Datasets. Since Luciddeamer is optimized for every input, we do not need training datasets to train the model. For the text input, we randomly generate several text prompts relevant to scene images to generate the first image using stable diffusion. We use real or generated high-quality images for the RGB input. For the case of RGBD inputs, we use ScanNet and NYU depth, since the two datasets have ground truth depth maps. Implementation details. The modules we used to construct Luciddeamer can either be trained using manual design or brought from off-the-shelf models. We use pre-trained large-scale off-the-shelf models to compose the whole network to maximize the generalization capability of the network. Specifically, we adopt stable diffusion model to inpaint the masked image. We use the same text prompt for the stable diffusion if the first image is generated from the text. If the image format is an RGBD image without text, we use LAVIS, L-A-V-I-S, to generate the caption according to the image and place it in the diffusion model to just content. For the camera trajectory that we use to construct the point cloud, P sub I for I equals
What happened? Is everything okay?
I just dropped off. How far along did I get before I dropped off?
They told me.
Is that I was just about to start 4.2 experimental results. Prior to that, I was talking about the implementation details. They used pre-calculated camera trajectories. Okay. 4.2 experiment results. We demonstrate the superiority and high generalizability of Luciddeamer in many aspects. We strongly recommend the readers to watch the video and supplementary materials where we can entirely show the strength of our model. V, do you have a link to the video that you could share with us?
I think V has departed and gone into lucid sleeping.
Oh. Oh. Isn't that sweet? I'll try and dig out the video later. Applicability to various input domain and formats. Luciddeamer is capable of generating a consistent and high-quality 3D scene, considering the input style. Figure 2 shows the generated realistic images and the 3D scenes. At the top row, we visualize a result of text to 3D. We depict an initial image generated from the given text and estimated depth in A. B and C represent the plausible images and geometry generated through our pipeline involving navigation, dreaming, and alignment. We showcase an overview of the final 3D scene in D. On the other hand, the bottom row demonstrates an example of RGB to 3D. We estimated depth from the given RGB and used it as an initial geometry for the scene. Similar to the top row, we generated believable images and geometry, resulting in a high-quality 3D scene. Since our model supports multiple images, it can generate 3D scenes in various ways, as illustrated in Figure 3. The top and middle rows depict the outcomes generated by guaranteeing the inclusion of conditional RGB during the creation of the 3D scene. Despite different texts, the conditioned RGB is consistently present in the scene. On the other hand, the bottom row displays the outcome of altering the text condition while generating the 3D scene. Through diverse combinations and alterations of conditions, our model facilitates the creation of the desired 3D scene more effortlessly. We illustrate additional example scenes in Figure 5. Our model successfully generates diverse 3D scenes with various styles, that is, Lego and anime, across different camera paths. And I'm going to take a look at Figure 3. Intermediate images during point cloud generation and final 3D input for different text prompts. We put the different text prompts while having the same initial image and compare the generated results. The first one, the images of a cat in a room, and the same image for all three prompts. The first prompt is a cat on the street near a white house with stairs, trees nearby, and gray blocks. The second one is a grass garden with bushes and flowers, white house with white stairs, table on the grass. And the third one is cat on the street near a house with stairs, trees nearby, and gray blocks. And the second prompt, a number of flower buckets, small bushes, and many pebbles on the ground. And all three generated images look consistent, though the first one has 3 cats, the second one has only 1 cat, and the third one has 3 cats. And knowing cats, they do Gaussian splat. Comparison with RGB D2. We qualitatively compare the generation results with RGB D2 and illustrate the result in Figure 4. For fairness of comparison, we compare the results on 3 images with different domains: generated image, ScanNet, and NYU depth. For the generated image, the depth map estimated by Zoe depth is considered a ground truth depth map when processing RGB D2. For ScanNet and NYU depth, we use the ground truth depth map for both RGB D2 and Luciddeamer when producing a 3D scene. For ScanNet, each scene consists of several images and the corresponding depth map and camera views. We randomly select one of the given image and depth maps pairs and use it as an additional RGB input. In Figure 4b, we observe that the RGB-D2 generates ScanNet-style images with similar styles regardless of the input image. This remains consistent not only in the initial image but also throughout the following sequence as seen in Figure 4c. We believe the issue arises due to insufficient training data and domain limitations, highlighting the need for a model with sufficient generalization. In contrast, our approach generates high-quality 3D scenes with careful consideration to harmonize well with the input RGB. Moreover, Luciddeamer can generate scenes composed of high-resolution images, while RGB-D2 can only make 128 by 128 sized images, which is too small to use in real applications. We also document the qualitative results evaluated in CLIP score and CLIP IQA in Table 1. We confirm that our model incorporates input conditions well, resulting in the creation of high-quality 3D scenes. And I'm going to back up and take a look at 4, which has 3 different conditions. The generated hours and RGB-D2 is the top two rows. The middle 2 rows are hours and RGB-D2 for ScanNet. And the last 2 rows are on NYU depth and hours and RGB-D2. In all cases, the Luciddeamer presents a good quality image across, including in cases where RGB-D2 is extremely fuzzy and not consistent and full of holes. And the Luciddeamer doesn't have any holes. The color is consistent across the images. The sharpness of the image is consistent. It doesn't wander off into a strange color region, which RGB-D2 does almost immediately. In general, it's just higher quality on every dimension that matters for image generation. And there's a video figure which we can't see. Ablation on design choices. We demonstrate ablation studies on the design choices of Luciddeamer. In Table 2, we compare the effect of call map initialization and the point cloud initialization provided by our method when learning Gaussian splatting. Luciddeamer achieved a high-quality scene within fewer iterations by offering a substantial amount of high-quality initialization points. Figure 6 illustrates the effectiveness of masking the image while learning Gaussian splatting. It removes the black splinter from the black background, resulting in visually pleasing outcomes. Figure 6, trained with a mask versus trained without a mask. Training with a valid mask helps prevent artifacts at the boundaries of scenes. And I'm not seeing what they're seeing here. I do see that the trained with mask has a black diagonal line, and trained without mask doesn't have that black diagonal line. But I don't see the artifacts at the boundaries they're referring to. Conclusion. In this work, we propose Luciddeamer, a novel pipeline for domain-free 3D scene generation. By fully exploiting the power of large diffusion models, Luciddeamer is capable of generating high-quality scenes without the restriction of the target scene domain. We first generate the point cloud from the input image and repeat dreaming and alignment algorithms to generate the multi-view consistent high-quality image and harmoniously integrate them to the existing point cloud in 3D space. After the construction is finished, the point cloud is converted to 3D Gaussian splats to enhance the quality of the 3D scene. Extensive experiments show that Luciddeamer can consistently generate high-quality and diverse 3D scenes in various situations. This is a really great paper and came so fast after Gaussian splatting.
Yeah, so basically the whole premise of this paper is, or like the whole pipeline is, you have a prompt, then you have a diffusion model that generates an image, then you apply depth estimation or monocular depth estimation to that image, then you pass all this into a Gaussian splat, and then you have a 3D scene. That's kind of like the whole premise of this. Overall, I'd say this is an 8 out of 10 paper. It would be a 10 out of 10 if they had code, but I don't think they do. They do not. That's unfortunate.
I think they've described it well enough for you to create it.
Yeah. Anything involving images is a little bit more difficult than anything with text. So it is. Things with images, and especially scenes, are much more difficult to implement than just text transformers stuff.
Yeah, they require a lot more training resources.
No, like the actual architecture and the code, like this has all been abstracted away to infinity and beyond. But like the actual code base for this might be really long and really complicated. But I'll try and see what happens. Lucid Range is probably gonna try to implement this as fast as possible because it has his name in it. That'd be quite.
He's good at that.
Yeah, I think.
It seems like it's fairly close to the paper we read right prior to the space generation paper, and that they're doing a similar kind of depth mapping. And I'd like to say it was the NERF paper. And there'll be code for NERF on the web.
Yeah. So
neural radiance fields.
What is the original 3D Gaussian splatting paper? 3D Gaussian splatting.
I don't know. I will dig it out.
Hugging Face has a whole blog on this. So basically, you have just data, and then basically Gaussian splatting just draws that data on some plane in space. That's all it does.
So the original Gaussian splatting paper was 3D Gaussian splatting for real-time radiance field rendering. It was presented at SIGGRAPH 2023. And it's a paper from a team at INRIA, the University de Côte d'Azur, and MPI Informatique. There is code for the original Gaussian splatting paper, which is here.
Yeah, I see. Interesting.
So that's 99% of what you'll need to implement this paper. The only other complicated part are the camera paths, which, well, you just pick some sort of path through 3D space to represent the camera path. And the extrinsics, which they don't actually describe thoroughly.
Hmm. The quality is insane.
Isn't it?
Wow. Gaussian splatting. There's 7,000 stars on GitHub.
It's a, it's a good technique. It took something which was extraordinarily compute intensive, namely neural radiance fields, and turned it into something which could run on consumer GPUs. It was really just an amazing improvement in computational speed and image quality and reduction of number of input images, and the result is just so much better.
Hmm.
And NERF was no more than 2 years ago. I can hardly wait to see the games that come out with this.
Yeah. Hmm. Hmm. Alright, well, that concludes tonight's paper reading. Hope you liked it and hope you learned something. This was 8 out of 10 paper. It would have been better if they had code, definitely. But the concept is really, really sound and very interesting and useful. So, yep. If you like to implement this, join Agora. We read papers every night at 10 p.m. New York time. And thanks for your time.